Hey guys, welcome back to chemistry. This week we're going to be talking about the atom and different models of the atom, and yeah. So today we're going to start off with talking about the Bohr model of the atom. So one of the experiments that shed light on atomic structure involved adding energy to atoms by heating them or passing electricity through them. And when that was done, the atoms emitted light, and some was in the visible spectrum. Each type of atom emitted its own unique color. And so, for instance, when mercury atoms were heated, a pale blue color would happen. And when neon atoms were heated, then it was bright pink that was emitted. And so, as chemists looked into this a little bit further, they learned that the colors emitted were actually the result of a handful of individual wavelengths of visible light being emitted by the atom. Most colors we see are the result of a range of wavelengths and not individual ones. So each element also has its own unique set of wavelengths that it produces when it's heated or electrified. And since each element will emit its own unique wavelength of light, you should be able to match the elements with their respective wavelengths and thus determine the composition of a substance. And this is the main way that astronomers, the scientists who study stars and planets and things like that, that's how they determine the makeup of stars in the distance. The reason that stars are bright is because the substances that make them up are very hot and they emit light. And they emit light in a lot of different wavelengths of light. But to our eyes, they appear white, because we talked about earlier how when we see a bunch of different wavelengths of light or all the wavelengths of light, that actually appears white to our eyes. There's a scientific instrument that's known as a spectrometer, and it can analyze the light and determine the wavelengths that make it up. And then by matching the elements to their expected wavelengths, the composition of the star can be determined. And this method is known as spectroscopy, and it also can be applied to chemicals. So the ability of atoms to emit individual wavelengths of light helped Niels Bohr determine or develop his own model of the atom. Rutherford assumed that all of the electrons orbited around the protons in a single orbit, and Bohr suggested that there were several possible orbits that the electrons could be in. And he also suggested that not only are there several orbits, but that they could jump between these orbits. And by the time that he had come up with his model of the atom, then the neutron had been discovered. And so Bohr put the neutrons and protons together in the center of the atom, and we call that the nucleus. So neutrons and protons in the center, and that is the nucleus, and then electrons orbiting around. One important advance that Bohr made in developing his model was the assumption that the electrons could only jump into and out of specific orbits. So if an electron decided to jump out of orbit 1, it couldn't just go anywhere, for instance. It had to go into another allowed orbit, such as orbit 2. It could not be anywhere in between. And this assumption is called quantum assumption. So how do electrons jump from one orbit to another? Well, the orbits that are far away from the nucleus require more energy. So if an electron wants to jump from an orbit that is close to the nucleus, we'll say orbit 1, to an orbit that is far away from the nucleus, or maybe like orbit 3, it can do so by absorbing energy. And this is what happens when you heat a substance or pass electricity through it. It's absorbing energy, and the atoms in the substance are absorbing energy. It allows the electrons to move from an orbit that's close to the nucleus to an orbit that's far away. And when this happens, we say that the electron has been excited. Now, if an electron would like to move from an orbit far away to an orbit close to the nucleus, so it's going the opposite direction, it's going toward the nucleus, the electron must get rid of its extra energy. So how does it do that? It does that by emitting light. So when an electron moves from an orbit far from the nucleus to an orbit close to the nucleus, we say it has de-excited. Thus, when you heat up a substance and its atoms emit light, you're witnessing a two-step process. So electrons in the atoms first gain energy because of the heat and move into orbits that are far away from the nucleus. And then after they sit in the far orbits for a short time, they decide that they'd rather be back in their original orbit. So they emit light in order to get rid of the excess energy and go back to their original orbit. And this is what makes the flames of a fire. So when you burn wood, the chemicals in the wood are first changed into carbon dioxide gas and water vapor via combustion. But heat is also produced. And the heat excited the electrons in the gases surrounding the fire, and they move to orbits farther away from the nucleus. But after being there for a while, they decide to de-excite back to their original orbit because they don't like to be excited for too long. And to do this, to go back to their original orbit, they have to emit light. And this is where the orange-yellow glow of the flames in a fire come from. Now, if you light a natural gas oven, you're going to notice that the flames are blue and not orange. And this is because the natural gas company purposefully contaminates its natural gas with a substance whose atoms emit a blue glow when excited. Since each orbit has specific energy associated with it, this means that the electron can only have certain energies. So, if it's in orbit 1, it has energy E1. If it's in orbit 2, it has another higher energy E2. So, very specific energies. Now, Bohr had detailed mathematical descriptions of the electrons moving in its various orbits for the hydrogen atom. He could use his math to determine the energy of each electron orbit, and he could determine how much energy the electrons needed to jump from one orbit to another. And then he could determine the wavelength of light that the electrons must emit in order to de-excite. And it turns out that the wavelengths he calculated were exactly equal to the wavelengths the chemists observed for de-exciting hydrogen atoms. And he was on the right track, and so his model gained acceptance. So even though today's accepted model of the atom is a little bit different from Bohr's model, his very detailed mathematics that he developed are still taught in college chemistry today. And additionally, the stylized pictures of atoms you see are actually really based on Bohr's model of the atom. All right, and that's all we're going to talk about today. Tomorrow we're going to talk about the quantum mechanical model of the atom. So we'll see you then.